Before engines conquered mountains and tanks crossed battlefields, one unlikely machine mastered something even harsher: deep winter in the frozen forests of Maine, where horses failed and industry stalled. A radical invention emerged, built to glide over snow and haul what nothing else could, turning winter into a highway for America's timber. If stories like this fascinate you, there's plenty more to uncover. Winter in Maine's logging country arrived without apology. Snowfall in the northern forest accumulated past 10 feet in the worst seasons, turning forest tracks into impassable trenches of white. The remote logging camps, pushing deeper into the interior every decade, faced conditions that made modern cold weather operations look comfortable by comparison. The timber industry had built itself around a seasonal rhythm that nature dictated. Loggers felled trees in autumn, then waited for enough snow to create the ice roads that made hauling possible. Horse teams dragging loaded sleds across carefully watered and frozen tracks represented the industry's best technology for most of the 19th century. And those roads required more labor to maintain than many small towns employed. Crews walked them every night with water barrels, flooding the surface to preserve the smooth ice that kept friction manageable. One warm day could destroy a week's work. The horses were the central problem. A good horse could pull perhaps 1.5 tons of logs under favorable conditions, considerably less in deep snow on a grade against real resistance. Teams of 4, 6, or 8 horses moved the loads that the biggest timber required, and those teams needed feed, care, shelter, and replacement when they broke down or froze. Every logging camp in the northern tier kept more horses than men, and the cost of feeding them through a Maine winter consumed profits that operators needed elsewhere. When the load was too heavy or the snow was too deep, the horses simply stopped. They stood still, breath rising in great clouds, legs trembling, and refused to move regardless of what encouragement was offered. Experienced teamsters knew exactly what the limit was and designed their operations around it. The forests within reach of those limits were already stripped bare by 1890. Everything beyond them waited. Railroad logging had solved part of this problem in the mountains of the West, where shay-geared locomotives climbed remarkable grades on temporary tracks and hauled timber that would never have moved otherwise. Shays were extraordinary machines built specifically for the slow-speed, high-torque work that logging demanded. But they needed tracks. Every mile of forest required a mile of iron laid first, and laying track through deep snow and frozen ground at the edge of nowhere consumed time and money that northeastern operators couldn't afford. The shay solved the grade problem without solving the snow problem, and in Maine, the snow problem was everything. The need was obvious to anyone paying attention. Something had to move through deep snow the way iron moved on rails, pulling loads that horses couldn't manage across distances that made ice roads impractical. Nobody'd built it yet, but Alvin Orlando Lombard was paying attention. One Maine machinist had been quietly watching all of this, and he was almost ready to change everything. Lombard was born in 1856 in Springfield, Maine, close enough to the logging operations that defined the regional economy that he understood the problem from childhood. He worked as a machinist and inventor, the kind of practical engineer that rural New England produced in quantity. Men who understood mechanism intuitively and approached problems with the confidence of people who fix things for a living. He'd watched those horse teams struggle on ice roads for years. He understood what a steam traction engine could deliver in raw power and what tracks could theoretically provide in weight distribution. The conceptual leap Lombard made around 1900 was connecting those two pieces in a configuration designed specifically for snow. His patent, filed in 1901, described a machine combining a steam boiler and an engine with a continuous cleated track system at the rear and ski-style runners at the front. The tracks would distribute the machine's weight across a large surface area, preventing the sinking that had defeated every other heavy machine that had tried it in deep snow before. The cleats would grip packed snow and ice without needing rails. The front runners could be steered. The steam engine would deliver sustained power that no other practical technology of that era could match. The genius was in the combination rather than any single component. Continuous tracks had appeared on experimental machines before. Steam power was decades old. Front ski steering was obvious to anyone who'd driven a sled. What Lombard had assembled was a machine where every design choice pointed toward the same goal: move the maximum amount of timber through the deepest snow over the longest distance with the smallest crew. The first production machines weighed between 20 and 40 tons, which was both a challenge and advantage. 40 tons pressing down on a continuous track spread that weight across an area large enough that the machine rode on snow rather than through it. The same 40 tons on wheels or hooves concentrated pressure that no frozen surface could support. The track was the key. Lombard had it right from the beginning. Now, the question was simple. Could this machine actually do what horses never could? A Lombard steam log hauler in its element was something people who saw it remembered for the rest of their lives. The machine stood perhaps 12 feet at the smokestack, with a boiler generating the steam pressure that drove pistons connected to the rear track system. Front runners, typically 8 feet wide, sat on the snow ahead of the boiler and connected to a steering mechanism the operator controlled from a position with reasonable visibility ahead and almost none to the sides or rear. The track was the defining feature. Wooden cleats, later replaced with iron, attached to a continuous loop of chain and cross members running along the bottom of the rear section. As the engine drove this loop forward, each section of track pressed down, gripped, and pushed back, advancing the machine exactly as a modern bulldozer track advances its machine. The physics were straightforward. The execution in 1901, built from available materials by a machinist in rural Maine, was remarkable. A fully assembled log train behind a Lombard challenged compression. A hauler connected to the first loaded sled, which connected to the second, extending down a train that could reach 30 sleds on favorable roads. Each sled carried perhaps 10 tons of timber, stacked and secured with chains by experienced loaders who knew how to balance weight across grades and corners. The 30-sled train behind one Lombard represented 300 tons of timber moving through a forest at speeds ranging from a walking pace on grades to 5 miles per hour on level road. The crew was small for what they were doing. An engineer managed boiler pressure and throttle, reading the machine's behavior through the controls and adjusting continuously for terrain. A fireman fed wood or coal into the firebox, managing the fire to maintain steam pressure in conditions that changed constantly. Working in heat from the boiler while the temperature outside sat at 30 below zero. A third man sometimes rode the front runners to scout the road ahead and warn of problems. Daily operations began before dawn. Boilers needed time to build pressure from cold, and a machine not ready at first light wasted the best cold hours when ice roads held firmest. Crews who had slept in logging camps within earshot of their machines started work in darkness by lantern light, performing the maintenance that kept equipment running in conditions that turned iron brittle and grease thick as putty. The loads they moved redefined what the industry believed possible. Documented hauls from peak Lombard operations include trains of over 300 tons moved several miles through weather that would have sent horse teams back to the barn. One record run in northern Maine during the winter of 1906 moved 280 tons of white pine over 7 miles of packed snow in a single day. Horse teams serving the same route had previously required 3 days for comparable loads, when conditions permitted movement at all. But moving timber faster was only part of the story. The real changes were happening to the entire industry around it. The economic transformation Lombard's machine delivered was immediate and measurable. A single steam hauler replaced between 30 and 50 horses along with their teamsters, feed costs, and care requirements. Capital cost was significant, but the operating economics made the purchase straightforward arithmetic for any operator running a substantial camp. The horses went away, the feed bills went away, and the loads got larger simultaneously. More significant than cost reduction was the access the Lombard opened. Forests beyond practical ice road range from rivers and rail connections had remained standing, not because anybody wanted to leave them, but because no economically viable way to reach them existed. The Lombard could work roads that horse teams couldn't maintain, cover distances that made those roads impossible with horses, and do it consistently enough that operators could plan around reliable winter output. Main operations expanded first. Within a decade of the first commercial sales, Lombard haulers were working in Michigan, Wisconsin, and Minnesota, where Great Lakes timber operations faced similar conditions and welcomed a machine delivering similar results. The lumber reaching American mills during the first decade of the 20th century moved in volumes that earlier generations of loggers would have found impossible. Cities growing across the continent consumed timber so fast that the industry needed every technological advantage to keep the supply up. The broader legacy reached further than any operator could have anticipated. Benjamin Holt, working in California on heavy agricultural equipment sinking into soft delta soil, was developing his own tracked tractor designs during the same period Lombard was refining his hauler. When the British military needed cross-country vehicles that could move through the churned mud of the Western Front in the First World War, the tracked tractor provided the mechanical foundation. The tank that emerged from that development drew on agricultural tractor technology that had drawn on log hauler technology that had drawn on Alvin Lombard's specific insight about what deep snow required. The chain ran from a Maine machinist watching horses fail on ice roads to armored vehicles crossing European battlefields within 15 years. Behind every remarkable machine, though, were the remarkable people brave enough to actually drive them. The operators who ran Lombard haulers occupied a specific place in logging camp culture that combined the status of skilled machinist with the reputation of someone willing to do something genuinely dangerous for a living. Engineers who understood their machines well enough to extract maximum performance while managing the risks were known across the regional logging community by name. Big Jack Morrison ran a Lombard on the Penobscot watershed for nearly 12 winters, building a reputation for moving loads in conditions that other operators refused to attempt. His machine was maintained to standards his peers considered excessive till they watched him haul through a late February storm that shut down every other operation on the river. Morrison understood that a well-maintained machine in difficult conditions outperformed a neglected machine in ideal ones, and he drove his firemen to the same standard of preparation he applied to his own work. Henry Bjornson ran haulers in Minnesota's timber country during the peak years of Great Lakes logging, working roads that crossed frozen lakes where ice thickness was never quite certain enough for comfort. Bjornson had calculated the weight distribution of his machine against the load-bearing capacity of lake ice with enough precision to take risks he'd mathematically verified rather than simply guessed. He was wrong once, losing a sled at the edge of a lake crossing in 1909. He was right enough other times that the loads he moved from stands accessible only across frozen water made him one of the most productive operators in the state. Thomas Nee worked in northern Wisconsin and left behind accounts from his crew describing a man who treated his machine the way experienced teamsters had treated their best horses, with attention to its sounds and behavior that bordered on intuition. Nee claimed he could tell from the sound of track engagement whether the ice road ahead was sound or beginning to deteriorate. His crew believed him because he'd saved his train from 2 road failures that should have been fatal based on nothing more than what he heard from the driver's position. These men didn't survive in any official record the way railroad engineers survived in company documentation. They existed in memories of crews who worked alongside them and in occasional newspaper accounts of remarkable hauls or notable accidents. The historical record of Lombard operations is thinner than the machines deserved, partly because the companies were small and private, partly because the work happened far from anyone taking notes, and partly because the men doing it regarded what they did as work rather than history. Of course, mastering these machines also meant learning to live alongside dangers most people never imagined. A steam boiler working at the pressures required to pull 300 tons through deep snow was not a forgiving piece of equipment. Boiler explosions were rare enough that operators didn't dwell on them, but common enough that everyone in the industry knew at least one account of a machine destroyed and a crew killed by a failure nobody'd predicted. Firemen maintained pressure within a range narrow enough to deliver power without pushing past what the boiler could safely contain. Doing this work in conditions where cold affected every measurement and exhaustion made precise judgment harder. The sled trains created their own hazards. Connection failure on a downgrade sent loaded sleds forward faster than the hauler could manage, and the weight of 300 tons moving under gravity rather than controlled power was something no machine or crew could stop quickly. Runaway events that began with a single failed chain connection could end with sleds piled against the hauler and logs scattered across the road. Cold at the temperatures common to Maine and Minnesota winters made every physical task more dangerous. iron became brittle at 30 below zero in ways visual inspection couldn't detect. Connecting pins showing no visible damage could fail under load because the metal had been weakened by freeze-thaw cycles nobody tracked. Crew members working 12-hour shifts in those temperatures accumulated cold exposure that impaired judgment in ways they often couldn't recognize in themselves. The forests these machines worked were being stripped bare as a direct consequence of how productive the Lombard made winter logging. The depth of forest that had previously protected remote stands from harvest disappeared when a machine could reach those stands economically. What generations of loggers had left standing because horses couldn't get there was gone within a decade of the Lombard's commercial success. The machine's greatest achievement and its greatest environmental cost were the same thing. Nothing this powerful lasts forever, and something new was already quietly arriving to replace it. The same forces ending the era of high horsepower steam on American railroads reached the logging camps of Maine and Minnesota during the 1920s. Gasoline and diesel engines delivered power without boilers, without firemen, without the preparation time steam required, and without the explosion risk that never entirely left any steam operator's awareness. Early internal combustion logging equipment was less powerful than mature Lombard designs, but it was simpler, cheaper to operate, and improving faster than steam technology could match. Better roads extended the reach of wheeled trucks into territory that had previously required tracked machines. The combination eliminated the specific application the Lombard had been built to serve, piece by piece, through the 1920s and into the 1930s. By 1935, steam log haulers operated in only a handful of remote locations where conditions still favored them over gasoline alternatives. By 1940, commercial operation had essentially ended. Several Lombard machines survived into museum collections. The example at the Patton Lumbermen's Museum in Maine represents the best preserved survivor, sitting in the state where it worked and where the problem it solved had been most acute. Yet, even after the machines fell silent, something far bigger and stranger lived on inside their tracks. Alvin Lombard died in 1937, having lived long enough to see internal combustion displace the steam technology he'd spent his career perfecting. He filed 12 major design revisions across his patent history, each incorporating feedback from operators who'd pushed his machines to limits he hadn't anticipated. The final Lombard designs were significantly more capable than the first, refined by the unforgiving testing environment of northern winters and the specific demands of men who depended on them for their living. The tracked vehicles that cross every difficult terrain on Earth today carry the mechanical inheritance of what Lombard worked out in Maine at the turn of the century. The bulldozer clearing construction sites, the military vehicle crossing broken ground, the snowcat moving through mountain wilderness, the agricultural machine working soft fields, all distribute their weight across tracks because the physics Lombard applied to deep snow apply everywhere that weight must be distributed rather than concentrated. America's timber drove the building of its cities, and the Lombard drove America's timber through the snow. That chain of consequence from a Maine machinist's 1901 patent to the lumber framing every building constructed during the first quarter of the 20th century represents a contribution that never received the recognition it deserved while it was happening. The men who ran those machines, the firemen who fed those boilers, and the crews who walked behind those sled trains in temperatures that made iron brittle built something that outlasted them all. The bold solve problems the cautious call impossible, and the machines they build reshape the world long after the steam is cleared. If that's the kind of history you're here for, hit that like button and subscribe for more.